Jai Hind to all. Today I am going to discuss the most important topic of power electronics, that is SCR. That means silicon controlled rectifier. Okay, silicon controlled rectifier. It is a part of thyristor family, right? So the contents that I am going to discuss today is the introduction of the SCR, what is its construction, what is its symbol, what is its structure, what are the VI characteristics of the SCR along with the different modes of operation, and if time permits I will discuss the switching characteristics of the SCR. So before starting with the SCR, before starting with the introduction of SCR, I would like to tell you about the history of the SCR. From where does it comes? What is actually SCR? Okay, so basically this SCR belongs to the family of semiconductor switches. Okay, semiconductor devices called thyristor, which was first introduced by the Bell Laboratories, okay, in 1957. Okay, so among the family, many semiconductor devices which just like GTO, just like PUT, just like DIAC, all these semiconductor devices, they have the similar characteristics as that of thyristor. So all these together will be called as the thyristor family. Now SCR is the part of that semiconductor family which is called as silicon controlled rectifier, right? And it is the most widely used semiconductor device among the thyristor family. So its use is so vast that the word thyristor is synonymous with the word SCR. Okay, so basically if we talk about the thyristor, then normally we are talking about the SCR. Okay, so basically that thyristor, from where does it comes from? The thyristor family or the thyristor. Okay, so basically it is a combination of two devices called the thyratron tube and the transistor. Okay, so the working of the thyristor is just like the transistor, and its characteristics and its operation is just like the thyratron tube, so it becomes the thyristor. Okay, now coming to the topic silicon controlled rectifier, that is SCR. Why it is so called? Because it is made up of the silicon and its operation will be like SCR. Okay, so it is will be like SCR, can be controlled. Okay, so it is called the silicon controlled rectifier. So this is the symbol for the SCR, and it is having three terminals: anode, cathode and gate, right? And it is having four layers PN along with the three terminals anode, cathode and the gate. Okay, so here you can say it is a 4-layer PN switching device having three terminals anode, cathode and gate. Okay, and it is having three junctions. Three junctions are J1, J2 and J3. Okay, so gate terminal is always connected near to the cathode terminal, right? And this SCR is basically a unidirectional device because just like diode, it blocks the current from cathodes towards the anode. Okay, so we can say it is SCR is having alternate P and 4 layers. Okay, so you can see here alternate P and PN layers, and the anode terminal is connected with the outer P layer, while the cathode terminal is connected with the outer N layer, and the gate terminal is always connected with the inner P layer, right? And this SCR can be modeled as the 2 transistor model. Its operation can be controlled as 2 transistor model also. Okay. So, in off state, it is having a very high resistance, while in on state, it is having a very small resistance. Right. So, this SCR was introduced in 1950s, 7, and since that, then it is having very high voltage rating of around 10 kilovolt and the current rating of 5000 ampere with the power handling capacity of 30 megawatt or more is possible nowadays. Right. So, this SCR is a very compact, very reliable, highly reliable device, and which is having a very small, that is called low loss solid state device. Right. As I told you, it works as a, its construction is a just like a transistor, which is a solid state device, right, and its operation is just like a thyratron tube. Now, due to these features, this SCR is universally employed for the controlling of power in the devices, both type of power, AC as well as DC power, right, and its application can be motor controls, time delay circuits, heater control, phase control, HVDC, etc., etc., etc. Okay. Now, the important thing for the SCR that they stay on once they are triggered, okay, and will go off only if the current is too low or when triggered off, right. Now, so this is a type of controlled rectifier in the sense that it has low resistance in the forward conduction and very high resistance in the reverse direction, okay, and it is controlled by the logic gate signal. See, once the SCR gets turned on, then it's cannot be turned off by simply pulling the gate signal. There are only two methods by which we can turn off the SCR, that is by applying a reverse voltage across the anode cathode terminal or by bringing the anode current below the holding current. I will later on explain you what is holding current and what is anode current. Now, the SCR, the characteristics of SCR, static VI characteristics of SCR are between the anode voltage and the anode current. Anode voltage and the anode current. Basically, there are three modes of operation of SCR when we are talking about the VI characteristics of SCR. First is the forward blocking state, which is also called as the off state, and then the reverse blocking state, and which is also again can be called as the off state of SCR, and then lastly third one is the forward conduction state, in the state in which the SCR will act like a switch which is on. Okay, so here I have, this is actually the conduction mode, this is the forward conduction mode here. So let's discuss these modes one by one. First of all, I'll discuss about the reverse blocking state. Okay, so what is the reverse blocking mode, right? See, I'll discuss this with the help of the 4 layers of the SCR, so that it can be easily understood. This is PN, PN. These are the 4 layers of the SCR. This is the anode terminal, this is the cathode terminal, and with the inner P terminal I have connected the gate terminal. Okay, so basically there are 3 junctions, J1, J2, and this is J3. So when a reverse voltage is applied between anode and cathode, okay, that means the junction, you can see this diagram for the better understanding of the VI characteristics. Okay, here in this diagram, I'll explain through this, but let me explain you this diagram how we will connect this with this. Okay, so here you can see that the SCR, the anode and cathode terminal are connected with the source voltage along with the resistive load, right? And the gate terminal and the cathode terminal of the SCR is provided with the another external supply called EG. Okay. Now, with gate circuit open with no supply to the gate to cathode terminal, I am talking about the reverse blocking state. Okay, when there is no supply between the gate and the cathode terminal and we have applied a reverse voltage. Sorry, reverse voltage means this must be negative and this must be positive. Okay. And when we have applied the reverse voltage between the anode and cathode terminal. Okay. So, that means anode is negative and cathode is positive. So, junction, here you can see junction J3, and since it is positive, it is negative. Junction J3 and J1 will get reverse biased here, and J2 will become forward biased. Okay, this will be reverse biased, these two junctions, and only junction J2 will be forward biased here. So, with because of this reverse biasing of the junction J1 and J3, no current will flow from anode to cathode or from cathode to anode, right? So, it will block the anode current, right? So, you can see only a very small leakage current called reverse leakage current will be flown in the circuit in the 4 layers of the SCR. So, this is represented by here. Okay? And now, if we so SCR will be in off state in this mode. This is the reverse blocking mode, okay, and SCR will be considered as the off state, in off state, right, and the very small current called the reverse leakage current is flowing here. Now, if anode to cathode voltage, this reverse voltage is increased to VBR. VBR here is the reverse blocking voltage of the SCR. Now, if voltage anode to cathode voltage is increased further equal to VBR or greater than the VBR, then a very high current will flow across that device, due to which the device may get damaged. So, this is the high current flowing across the device represented by the PQ. Right. So, we have to, because the permissible temperature of the device may get exceed, due to which a very high current flow across the device which may damage the device. So, we have to take care that the voltage reverse anode cathode voltage will not exceed the reverse breakdown voltage, that is VBR. Okay. So, this is the reverse blocking mode. So, you can see in the reverse blocking mode, when I have applied the reverse voltage between anode and cathode, that the two devices, two diodes, PN and PN, they are simply connected in series with each other, right? And this junction, when I have applied a voltage greater than VBR, right, an avalanche will occur at the junction J1 and J3, due to which a large current will flow across the device, right. This large current may exceed the permissible temperature of the device, and which ultimately damage the SCR. Okay. So, this is actually the reverse blocking mode, right. Now, coming to the forward blocking mode, it is represented by O and M, right. So, in the forward blocking mode, we have applied the voltage anode and cathode voltage. I am changing here. Again, with gate circuit open, I am applying voltage between anode and cathode, with anode as positive and cathode as negative. Okay. So, here. So, in this case, you can see that the junction J1 and in this case, junction J1 and J3 are forward bias now. These two are now forward bias, and junction J2 is here reverse bias. Okay. So, the junction is J2, since here is reverse bias, the switch will again behave as a off state, and no node current will flow. Only a forward leakage current of the few milliamperes will flow in this mode, right. Now, when a voltage greater than VBO, which is called as the forward breakover voltage. When a voltage, anode voltage is exceeded or equals to VBO, the device immediately get turned on and the point M at once shifted to point N and then anywhere between N and K. Okay. So what happened when I have applied a voltage greater than VBO, then avalanche will occur at the junction J2, right, and which will allow a large current to flow through the device. So in the characteristics you can see in the characteristics you can see in the OM mode that the device offers a very high impedance, due to which the low current is flowing in the circuit and the the device will behave as a closed switch. Similarly, in the reverse blocking mode, a very high impedance is offered in the reverse direction due to the low current, due to which the device will behave as a off circuit, right. Now, when I am talking about the forward conduction mode, so in this mode the SCR will get turned on, right, it will behave as an on switch. Now, here you can see a very small voltage drop across the device will occur with a very high current, and as the value of the anode current is increasing, the voltage drop slightly increases across the device. So you can see I have shown the two currents called the latching current and the holding current in this characteristics. So this is the latching current and this is the holding current. So the value of latching current is greater than holding current always, right. So the latching current is the minimum current which is required to keep the SCR in the on state. And this is holding current. This holding current is the minimum current which is required to keep the SCR, to bring the SCR in the off state. Okay. So if we want to turn off the SCR, if we want to turn on the device, then we can either apply the reverse voltage across the device, or we can try to bring the anode current below the holding current. Okay. So these are the three modes of the operation of SCR during the VI characteristic, in which only forward conduction mode can be called as the on state of the switch, while in these two modes the device will behave as a off switch. So I have explained here, I have written the definition of the terms that I have used in the characteristic. First of all, the forward breakover voltage. So forward breakover voltage at which SCR will enter into the forward conduction mode, right. If I increase the anode voltage equals to forward breakover voltage or greater than the forward breakover voltage, then SCR will at once shift to the forward conduction mode, right. Now, the holding current, I have told you, holding current is the minimum value of the anode current which is required to maintain the SCR in the on state, right. After that, the SCR has been turned on. If I reduce the value of anode current below the holding current, then SCR will get turned off. And the latching current is represented by IL. It is the minimum value of anode current which is required to keep the SCR in on state at the time when SCR is already turned on, right. Now, the gate trigger current, it is the value of the gate current to switch on the SCR. See, I have told in the forward blocking mode and the reverse blocking mode, here the gate switch is kept open, while when we talking about the forward conduction mode, in this mode this gate switch is closed. That means I have applied a voltage EG between the gate and the cathode terminal. Okay. So it is the value of the gate current to switch on the SCR. Now, what is the average forward current? Average forward current is the maximum continuous anode current that can, it is the maximum continuous anode current, or you can say DC current, that the SCR can withstand during its working, right? And the reverse breakdown voltage is the maximum reverse voltage before SCR breaks into avalanche, and the current will exceed its permissible value, temperature will exceed its permissible value, and the very high reverse current will flow across the device, due to which the device may get turned on. Okay, so these are the some terms which are related to the VI characteristics of the SCR. Okay. Now coming to the switching characteristics of the SCR. See, basically the switching characteristics of the SCR are representing the turn on and the turn off states of the SCR. Okay. So the characteristics are, how come not properly visible? Okay. This is the anode voltage and the gate current, and this is the cathode anode current. Okay. So you can see here that the turn on time, basically in the switching characteristics, it is divided into two parts, the turn on time and the turn off time. And turn on time is further divided into the delay time, the rise time and the spread time. And turn off time is divided into reverse recovery time and the gate recovery time, right? In the turn off time, there are basically two turn off time. One is TQ, which is the device turn on time, and one is the TC, which is the circuit turn off time. Okay, so here you can see TQ is representing the turn off time for the SCR, while this TC is representing the turn off time for the device in which the for the circuit in which the SCR is connected. Okay, so starting with the turn on time means the SCR is in the forward conduction state, right? So basically turn on time is the time when the SCR moves from the forward off state towards the forward on state, right? And turn off time is when SCR moves from turn on state to turn off state, that means forward conduction state towards the forward blockings mode. Okay. So turn on time, in turn on time, this delay time can be represented by this, that time, this is the delay time, this is the rise time, and this is the spread time. Okay, so you can see here delay time can be defined as the time during which the gate current reaches 0.9 Ig to the instant the anode current reaches 0.1. This is 0.1 Ia. Here gate Ig and gate current Ig and the anode current Ia are representing the final values of the gate current and the anode current respectively. Okay, or we can define the delay time as the time during which the anode current reaches from a small leakage current towards the 0.1 of Ia, that is 10% of the anode current. Or we can define the delay time as the time during which the anode voltage falls from the initial value of the anode voltage towards the 0.9, this is 0.9 VA, that is 90% of the anode voltage. Now, the rise time can be defined as the time the SCR taken, that the SCR take from rise time can be defined as the time during which the anode current rise from 0.1 Ia to 0.9 Ia, that is from 10% to 90% of the anode current, or in terms of anode voltage, it falls from 90% towards the 10% of anode voltage. During the spread time, the anode voltage finally falls from 0.1 VA to on state voltage drop, right, minimum voltage, and the anode current rises from 90% to the final 100%, that is IA. Okay, so this is the turn on time of the SCR. Now after completing the turn on time of the SCR, the anode current will be IA and the voltage VA will be the minimum on state voltage drop across the SCR. Now the turn off time is finally started from the time when the anode current reaches the value called 0, right? And the during the turn off time, when it is divided into TRR and TGR, you can say during the turn off time, the excess carriers from all the 4 layers of the SCR are removed, right? So during T1 to T3, which is represented by TRR, it is called as reverse recovery time, right? Junction from the outer junction J1 and J3, excess carriers from the outer layers are removed. Outer P layer, holes from the outer P layer and electrons from the outer N layer are removed from during the time T1 and T3. At T2, when about 60% of excess charge carriers are removed from the outer layers, right, reverse current will at T2 around 60% of the carriers are removed from the outer 2 layers. Okay. After T1, you can see the IT, the anode current build in the reverse direction with the same slope as that of before T1. Okay. Now junction excess carriers at the junction T2 will be removed during the time T3 to T4, and it is possible only with the help of the recombination. The excess carriers from the junction J2 can be removed only recombination process, right? During the time when the reverse current is built up in the circuit, a reverse surge voltage is also developed in the circuit, right? And for the recombination purpose, this reverse voltage, although it will not be good for the circuit, but because of recombination, reverse voltage, surge voltage must be maintained across the device, right? And the magnitude of the voltage is not required, but there must be some reverse surge voltage across the device so that the recombination process may take place and excess carriers from the junction J2 may be removed, right? And at T4, when all the excess carriers are between the instant T3 and T4, when all the excess carriers from junction J2 are removed, the circuit, that is, sorry, the device may get turned on, right? And T4 to T5 is the time when the circuit gets turned off. Okay. So basically the turn off time is divided into TRR plus TGR, and which is further a combination of TQ plus TC, and TRR plus TGR is a combination of TQ, which is the turn off time of the SCR, and TC is the circuit turn off time. Okay. So I hope this is clear to all, and I'll discuss further the examples based on SCR in the next lecture. Thank you so much.